Howdy. We're going to continue on with our protein sequencing, our 6-step protocol, starting now with step 3. In step 3, the object is to identify the amino terminal and carboxy terminal amino acids of our polypeptide. Remember, in steps 1 and 2, we separated the 2 polypeptides, and from here on out, we're just going to be working with one of the polypeptide chains. For example, insulin has 2, so we have to do these steps twice. All right, so you've got one polypeptide chain, and when all is said and done, you're going to want to recapitulate the first and last amino acid, because if they match step 3, then you've done your reconstruction of the full sequence correctly. So that's what we're doing in step 3. We already know a reagent, a chemical reagent, that works to identify the amino terminal amino acid, and that's the phenylisothiocyanate that we call Edmonds reagent. And Edmonds reagent gives you 2 products. The first amino acid, or the amino acid at the N-terminus, is part of this PTH derivative, and of course the other product is the rest of the polypeptide chain, starting with amino acid 2 as its new N-terminus. This reaction would have to be repeated a number of times in order to get sequential removal of each new N-terminus, and that works for very, very short peptides, but the yield is poor, and so you can't really go much farther than, say, 10 amino acid residues. And we will use Edmonds reagent as a tool in your toolbox to give us the sequence of shorter polypeptides, really oligopeptides, that we get from our cleavage reagents in step 4 and 5. So we'll use Edmonds reagent here in step 3, but keep it in your toolbox for steps 4 and 5 when we do some sequencing of shorter fragments. Okay, in addition, we want to know the C-terminal amino acid, and we don't have a chemical for that. Instead, we have an enzyme, a protein that recognizes the C-terminus of a protein, of another protein, and is able to catalyze the addition of water across the peptide bond between the second to last amino acid and the last amino acid. The last amino acid is not connected to another amino acid with a peptide bond, so it's going to cleave the peptide bond before the last amino acid, okay? So the way that carboxypeptidases work is they bind the C-terminus and catalyze the addition of water across that peptide bond before any C-terminal amino acid except proline, arginine, or lysine if you're carboxypeptidase A. So in other words, carboxypeptidase A is used to cleave off the last amino acid, but it won't work if your last amino acid is proline, arginine, or lysine. Okay, so you tried your carboxypeptidase A and you got no product. So then you move on to the second tool that you have for C-terminal analysis, and that's carboxypeptidase B. And B works only if your C-terminus is arginine or lysine, not any other amino acid, okay? It won't work for proline. It won't work for anything except arginine and lysine. So if you have some good controls that tell you that carboxypeptidases A and B are both working as they should, and you've already tried carboxypeptidase A and you got no product, so you go to carboxypeptidase B and you still have no product, then what does your C-terminus have to be? That's right, proline, okay? All right, so add these tools to your toolbox, and you're going to use them to identify, as I said, the amino terminal and carboxy terminal amino acid. If we look at the reaction for the Edmonds reagent, and for those of you who are chemists, you might enjoy understanding the nucleophilic attacks that are involved that give you the products, and that's why I show it here, not because I want you to memorize it, but just to give you a chemical rationale for why this works. Okay, so what you're seeing is the nucleophile is the amino group. That's why it works on the amino terminus. It has a free amino group, which attacks the carbon here in the isothiocyanate. And then the amino group that's part of that new covalent bond attacks the carbonyl-like sulfur-containing carbon. And then there's an anhydrous reaction that gives you a derivative, and this is not yet our final PTH derivative. And here is your other product. Your first product really is the rest of the polypeptide chain without its original N-terminus. Instead, amino acid 2 is the new N-terminus, and here's the free amino group. The last step is a weak acid reaction, which converts this derivative into the PTH amino acid derivative. And you can see that the R1, everything in blue was amino acid 1, and R1 is a functional group hanging off of the ring structure. And this can be identified chemically or by mass spec by a lab other than yours. So you're going to send this out, and they're going to tell you what your amino acid was in your PTH derivative. And then you're going to either discard this part of the protein, or if your sequencing is short oligopeptide, you might repeat with fresh Edmonds reagent and sequence a few more amino acids. But for all intents and purposes, we're done in step 3 once we've isolated and identified this product. In steps 4 and 5, we're going to fragment the chains using cleavage reagents. Cleavage reagents can be chemical, or they can be enzymes that are very specific to cleave after a given amino acid. And that's what is shown here at the first bullet point. 3 enzymes that I want you to get to know very well that catalyze the addition of water after a specific amino acid: trypsin, chymotrypsin, and staph protease. And one chemical reagent is going to be added to your toolbox as a cleavage reagent, and that's cyanogen bromide. Okay, so we're going to cover each one of those. All right, trypsin is specific for addition of water across the peptide bond that follows a lysine or arginine amino acid. That's what's meant by the C-terminal side. It's the peptide bond after the lysine and the arginine. Remember how I said carboxypeptidases cleave the peptide bond before the C-terminal amino acid? Well, all the rest of these cleave after the amino acid. Okay, so that's going to be true for all of these. All of them cleave on the C-terminal side. Trypsin, basic amino acid, is specific for basic amino acid, aids the addition of water on the peptide bond following lysines and arginines. Chymotrypsin aids the addition of water across the peptide bonds following a phenylalanine, a tyrosine, or a tryptophan. Occasionally, you'll get leucine, cleavage after a leucine, so large nonpolars or aromatics. We aren't going to study clostropane. We already have trypsin. Staph protease is interesting, and it can be exploited because of its unique specificity. It cleaves after the acidic amino acids at pH 7. So it'll cleave the peptide bond following a glutamic acid or an aspartic acid. But if you go to pH 5 or to pH 10, buffering either an acetate or bicarbonate, if you remember how buffers work, then it will only aid the cleavage of the peptide bond following the glutamic acid. And that might help to reduce the number of fragments that you have to analyze, because you have lots of aspen glues in a protein, and so you might want to choose to just cleave after glutamic acid. You'll see why in a few minutes. So you'll want to add these enzymatic cleavage reagents to your toolbox. This is an example of how trypsin works. Here's water. This is a hydrolysis reaction, so it's going to consume a water. And the water is added across the bond, this bond right here, the carbonyl side of the lysine or arginine side chain. This one is the lysine, and the amide bond after that is what's cleaved. And you'll get a new amino terminus on the black part of the polypeptide chain, which continues on, and you'll cleave with a new C terminus containing the lysine or the arginine, after which it was hydrolyzed, right? And then, of course, this would go towards the N terminus on this side. Know the products of hydrolysis. So if you had a polypeptide, here's a short one, that is color-coded so that it looks like the basic amino acids are in blue. Wherever you have a basic amino acid, arginine or lysine, trypsin will catalyze the cleavage after that. And so you'll have these 4 amino acids at the N terminus of this short oligopeptide, this one, this dipeptide, this one, and this one. But if there are hundreds of thousands of these in your reaction vial and they're all mixed together, we wouldn't be able to recapitulate the sequence, right? It could be in any order. And that's why we need step 5. But we'll hold off on step 5 for now while I give you your last cleavage reagent, a chemical cleavage reagent, cyanogen bromide. CNBr acts only on methionine residues, and it cleaves by cyclizing the methionine side chain. It's useful because methionines are not very abundant in most proteins, and so you don't get a lot of different products. We will look at the reaction with cyanogen bromide and its 2 products, a peptide with a C-terminal homoserine lactone where the methionine used to be, and the rest of the amino acid sequence after the methionine. This is the reaction here. The cyanogen bromide is shown in red. It's a nucleophilic attack with the bromide leaving group, and the product is shown here. There's another reaction, another nucleophilic attack. The several steps are shown in one here. Please don't memorize the reaction unless you want to. And then ultimately there's a hydrolysis reaction that gives you the peptidyl homoserine lactone for everything up to the methionine. So this used to be, what's in green used to be the methionine. And the polypeptide after the methionine and on to the C terminus or to the next methionine is shown as the second product. So knowing the 2 end products are what you should know and where it cleaves. And so this is your toolbox. These are your reducing agents, DTT and beta-ME, which are used together with the iodoacetate, that alkylating agent that irreversibly inactivates the cysteines. Carboxypeptidases A and B for the C-terminal amino acid identification, and Edmonds reagent for the N-terminus. Trypsin, chymotrypsin, and staph protease are your enzymatic cleavage reagents, and cyanogen bromide is your chemical cleavage reagent. Now we're going to, in the next video, perform this cleavage and analysis one more time and show you how you can deduce the full sequence by comparing the fragments that you get back and aligning the sequences.